Now coming to the coupled engines. Now what is a coupled engine? If we are joining two or more engines in series, that becomes a coupled engine. For example, in this particular case, we are having two engines, engine 1 and engine 2. These are joined in series. Now what do you mean by engines are joined in series? So we are having two temperature reservoirs T1 and T2. Between this both the engines will work, and in between we are taking an intermediate temperature which is at temperature T. Okay. Now this engine 1 is taking heat from high temperature source, Q1 heat is taken, this engine is taking Q1 heat from high temperature source, Q heat is rejected to the intermediate temperature source, and in this process this engine is performing the work W1. Okay. And as we know, this W1 obviously will be equal to Q1 minus Q. Getting this? Okay. Now the heat which this body was taking, this Q heat which this body which is at temperature T, intermediate temperature body was taking, with the help of this same heat, now we are running engine 2, we are running second engine. So this second engine is taking heat Q from this intermediate temperature source, rejecting Q2 to the lower temperature sink, and in between this is performing the work W2, and obviously this W2 from here will be equal to Q minus Q2. Okay, so I think the arrangement is clear. So the total work which we will get from this complete cycle, this complete process, this complete coupled engine, total work will be equal to W1 plus W2. Total work will be work done by engine 1 plus work done by engine 2, first thing. Now what would be the efficiencies? We are assuming these two engines as the reversible engines. Okay, now what will be the efficiency of engine 1? Okay, so this is operating between temperature T1 and T. Okay, so the efficiency of engine 1 will be equal to 1 minus T by T1. Lower temperature here is T, higher temperature is T1, so this will be 1 minus T by T1, first thing. Getting this? Similarly, efficiency of engine 2, this will be equal to, so engine 2 is operating between T and T2, so this will be equal to 1 minus T2 by T. Getting this now? Now further, this efficiency of engine 1, now because the W1 work is done by taking Q1 amount of heat by this engine 1, so this efficiency of engine 1 can be also written as W1 by Q1, yes or no? Work done divided by heat transfer. Similarly, this efficiency of engine 2 can be written as W2 by heat transfer, which is Q in this particular case. Okay, or you can say this from here, this W1 by Q1 will be equal to T1 minus T by T1, and W2 by Q, this will be equal to T minus T2 by T. Clear or not? Okay. Now we will consider two different cases, and with the help of those cases we will try to find out this intermediate temperature. What will be the value of this intermediate temperature? Now the first case is for equal work output. Okay, that means if W1 is equal to W2, if the work output from the both engines are equal, then what will be the value of this, or what should be the value of this intermediate temperature T? Okay, so for this W1 should be equal to W2. Okay, so just put the values. So this will be equal to what? Q1 minus Q is equal to Q minus Q2. Okay. Now further this can be written as Q1 by Q minus 1 is equal to 1 minus Q2 by Q, dividing this by Q. Now this Q1 by Q, because this is a reversible engine, can be written as T1 by T, and this Q2 by Q can be written as T2 by T. Okay, so this will be equal to, from here this will be equal to T1 by T is minus 1 is equal to 1 minus T2 by T. Okay, so from here this will be T1 plus T2 by T, this will be equal to 1 plus 1, which is 2, or you can say T intermediate temperature is equal to T1 plus T2 by 2. Okay. So for equal work output cases, total temperature, intermediate temperature T will be equal to T1 plus T2 by 2. Okay. Or you can say the intermediate temperature will be the algebraic mean of the two temperature T1 and T2. Getting this or not? Okay. Now for second case, we are taking for equal efficiencies. Okay. Initially we have taken it for equal work output. So for equal work output, we got the conclusion that the intermediate temperature T should be equal to the algebraic mean of the two temperatures. Now what about for equal efficiencies? So if eta 1 is equal to eta 2, now what will happen if eta 1 is equal to eta 2? Now eta 1 is equal to 1 minus T by T1, eta 2 is 1 minus T2 by T. Okay. So this 1 will be cancelled out, and we will get what? So this will be equal to T2 minus again cancel out, this will be T2 into T1 is equal to T square, or you can say T is equal to under root of T1 T2. Okay. So for equal efficiencies, the intermediate temperature is equal to root of T1 T2, or you can say geometric mean of the two temperature. Under root of T1 T2 means geometric mean, T1 plus T2 by 2 means algebraic mean. Okay, so for equal work output, very important conclusion, for equal work output in a coupled engine, the intermediate temperature T is algebraic mean of the two temperatures, and for equal efficiencies, intermediate temperature T is the geometric mean of the two temperatures. Clear? Okay, so now coming to the overall efficiency of this coupled cycle. Overall efficiency. Okay, now what will be the overall efficiency? Now if you see this properly, you will find that this is as good as the engine which is working between two temperature limit T1 and T2. Okay, so I can redraw it as, this is an engine which is working between the temperature limits of T1 and T2 and which is producing total work W1 plus W2. Getting this? Now what will be the overall efficiency of this complete cycle? So this will be obviously equal to 1 minus T2 by T1. So overall efficiency of the coupled cycle will be 1 minus T2 by T1. Okay, now further we can write it as, now this T2 by T1 can be written as, this can be written as T2 by T into T by T1, multiplying and dividing by T, T2 by T into T by T1. Okay, now what is this T2 by, now this T2 by T1, this from this equation, this T2 by T1 can be written as 1 minus eta naught. Okay, T2 by T1, eta naught is 1 minus T2 by T1, so T2 by T1 is 1 minus eta naught. This will be equal to T2 by T. Now what is this T2 by T? So this T2 by T can be written as 1 minus eta 2, and this T by T1 can be written as 1 minus eta 1. Okay, so this 1 minus eta naught will be equal to 1 minus eta 1 into 1 minus eta 2. Getting this? Okay, further if you solve this, you will get what? Eta naught is equal to eta 1 plus eta 2 minus eta 1 eta 2. Clear or not? That means if you are having the efficiencies of individual engines, if you are having the individual efficiencies of the engine, you can determine the overall efficiency by using this formula. Eta naught is equal to eta 1 plus eta 2 minus eta 1 eta 2. Getting this or not? Okay, this for two engines. What if I am having three engines? Okay, so for three engines, now what will be the formula for overall efficiency? So this overall efficiency we can determine by using this 1 minus eta naught. This will be equal to 1 minus eta 1, 1 minus eta 2, 1 minus eta 3. Okay, इसको ऐसा मत कर देना कि eta naught is equal to eta 1 plus eta 2 minus plus eta 3 minus eta 1 eta 2 eta 3. Okay, no, that would be wrong. Simply इस फॉर्मूले हमको रिप्लेस करना है 1 minus eta naught is equal to 1 minus eta 1, 1 minus eta 2 into 1 minus eta 3. This is the overall efficiency for the coupled cycle. Getting this or not? Okay. Now few very important conclusions which can draw from here. The very first conclusion is, now let's suppose I am explaining you with the help of one example. Let's suppose efficiency of engine 1 is, let's suppose 40% and efficiency of engine 2 is, let's suppose 30%, 0.4 and 0.3. So what will be the overall efficiency? So this will be equal to 0.4 plus 0.3 minus 0.4 into 0.3. Okay, so this will be 0.7 minus 0.12, so this will be 0.58. Okay, now what conclusion can we draw from here? The overall efficiency of the cycle will always be greater than that of the individual efficiency. If you want, you can take another example as well. Okay, always you will get what? The overall efficiency of the engine will always be greater than the individual efficiency. Here overall efficiency is 0.58, individual efficiencies are 0.4 and 0.3. So overall efficiency of the engine will always be greater than the individual efficiencies. First thing. Second very important conclusion we are drawing it from here. Just understand this thing very carefully. What we are doing here is, हम इसमें क्या कर रहे हैं? We are connecting two engines in series. Okay. That means first we are having Q1 amount of heat. We have withdrawn certain work from it. Q amount of heat is transferred to this intermediate temperature. Then from here again we have drawn certain work on it and remaining heat was transferred to the lowest temperature. Now what if I am increasing this number of engines? If I am increasing this number of engines over and over again, अगर मैं इस number of engines को मैं बढ़ाते जा रहा हूँ, then what will happen? So just understand this thing that every time I am getting certain work और जो remaining heat मुझे मिल रही है, उसमें से फिर से मैं कुछ work withdraw कर रहा हूँ and then remaining heat is transferred to the next engine and so on. That means suppose I am having the temperature T1, I am having heat Q1, okay, this is engine 1, this is transferring heat suppose Q2 to temperature T2, then from here this Q2 will run another engine E2 rejecting Q3 to temperature T3, then this will run another engine E3 and so on. Okay, if I am putting n number of engines, बहुत सारे number of engines if I am putting this on series, then what will happen, then where am I approaching? Okay, so जितना यहाँ पर suppose Q1 amount of heat है, इसमें से हमने कुछ work draw किया, then Q2 amount of heat इसमें reject हुआ, फिर इसमें से हमने कुछ work draw किया, फिर Q3 amount of heat इसमें reject हुआ, फिर इसमें से हमने कुछ work draw किया. That means if I am putting suppose infinite number of engines in series, if I am increasing the number of engines in series, then what will happen, then at a certain point this whole work done, that means the heat rejected, क्योंकि अब ये Q2 की वैल्यू धीरे धीरे कम होते जा रही है. For example, suppose here this Q2 is suppose 50 kilojoule. Out of this I am withdrawing 25 kilojoule of work और यहाँ बचा कितना 25 kilojoule. Okay, now from this 25 kilojoule, let's suppose I am withdrawing again 10 kilojoule of work. Okay, and remaining heat here is 15 kilojoule. अब इस 15 kilojoule में से जब मैं इसमें suppose 5 kilojoule of work I am extracting, then remaining would be, then this here this Q2 would be 10 kilojoule. That means this Q2 की वैल्यू heat rejection की वैल्यू जो है वो continuously decrease होते जा रही है. और एक पॉइंट ऐसा आएगा, इफ आई एम डिक्रीजिंग दिस कंटिन्यूसली, इफ आई एम पुटिंग मोर एंड मोर इंजिन्स इन सीरीज, एक पॉइंट ऐसा आएगा वेयर दिस Q2 विल बी इक्वल टू 0, हीट रिजेक्टेड विल बी इक्वल टू 0, एंड एट दैट पर्टिकुलर पॉइंट ऑब्वियसली द टेम्परेचर विल ऑल्सो हैव टू बी 0. इफ द टेम्परेचर, क्योंकि लोएस्ट टेम्परेचर कहाँ तक जा सकता है, बिकॉज दिस टेम्परेचर इज कंटिन्यूसली डिक्रीजिंग, लोएस्ट कहाँ तक जा सकता है, दिस कैन बी अप टू 0 केल्विन ऑफ टेम्परेचर. ये कहाँ तक जाएगा, अप टू 0 केल्विन ऑफ टेम्परेचर. So at that 0 Kelvin of temperature, this Q will be equal to 0, heat rejection will be equal to 0. Okay, so if I am achieving that point, obviously this total heat Q1 will be equal to the total work done. That means total work done मतलब W1 plus W2 plus W3 and so on. Okay, तो ये क्योंकि because ultimately heat rejection यहाँ पर 0 हो गई है, तो जितनी भी heat मैंने दिया है वो पूरा किस में कन्वर्ट हो गया है, वो work में कन्वर्ट हो गया है. But according to Kelvin-Planck statement of second law, this particular thing cannot happen because this would become PMM2, perpetual motion machine of second kind, which according to second law of thermodynamics, Kelvin-Planck statement of second law of thermodynamics to be more precise, which according to Kelvin-Planck statement of second law of thermodynamics is impossible. Now this means कि अगर ये चीज़ पॉसिबल नहीं है, इसका मतलब क्या हुआ, इसका मतलब ये हुआ that achieving 0 Kelvin is impossible. क्योंकि अगर किसी भी पॉइंट पे अगर मैं 0 केल्विन अचीव कर लेता हूँ, देन दिस इंजन वुड बिकम PMM2. जितनी हीट उसमें हम दे रहे हैं वो पूरा का पूरा वर्क में कन्वर्ट कर रहा है, इफ आई एम अचीविंग 0 केल्विन एट ऑल, एंड विच विल वायलेट दिस सेकंड लॉ ऑफ थर्मोडायनेमिक्स, केल्विन प्लैंक स्टेटमेंट ऑफ सेकंड लॉ ऑफ थर्मोडायनेमिक्स. सो दिस पर्टिकुलर थिंग इज नॉट पॉसिबल, PMM2 is not possible, therefore achieving this 0 Kelvin is not possible. Very very important thing. And this actually became the थर्ड लॉ ऑफ थर्मोडायनेमिक्स. थर्ड लॉ ऑफ थर्मोडायनेमिक्स का एक स्टेटमेंट ये है दैट बाय एनी मीन्स इट इज इम्पॉसिबल टू अचीव 0 केल्विन टेम्परेचर. 0 केल्विन टेम्परेचर अचीव करना पॉसिबल नहीं है. दैट मीन्स नो वेयर यू विल गेट दिस 0 केल्विन टेम्परेचर. ओके, वेदर यू गो टू अंटार्कटिका और एनी वेयर इन द वर्ल्ड और एनी वेयर आउटसाइड वर्ल्ड, द टेम्परेचर बिलो 0 केल्विन टेम्परेचर के अटेन करना इज नॉट पॉसिबल. Getting this not? Okay, so this actually is the third law of thermodynamics. So you can write down the note. First law is a quantitative law, second law is a qualitative law. It imposes a limitation on amount of heat that can be converted to work. Second law is a directional law. Next note, if enough engines are placed in series to make the work output is equal to Q1, then by first law heat rejected from last engine will be 0. By second law, however, the operation of cyclic heat engine with 0 heat rejection cannot be achieved. When heat rejected approaches 0, the temperature of heat rejection also approaches 0 as a limit. Thus, a definite 0 point exists on the absolute temperature scale, but this point cannot be reached without violation of second law. Next is third law of thermodynamics, which says it is impossible by any procedure, no matter how idealized, to reduce any system to the absolute 0 temperature in a finite number of operations. Next, coming to the Carnot coupled refrigerator. Okay, so we are having इन द सिमिलर वे हमने जो देखा कि कपल्ड इंजन जैसे हमने देखा, सिमिलर वे में हम कपल्ड रेफ्रिजरेटर देख रहे हैं. वी आर कनेक्टिंग टू रेफ्रिजरेटर्स इन सीरीज. Okay, this is the lowest temperature body which is to be maintained at this temperature as is the function of refrigerator. T2 temperature हमको maintain करना है, and for this we are connecting two different refrigerator. First refrigerator R2 is taking heat Q2 from this sink. On doing work W2, this is rejecting heat Q to the intermediate temperature T. So this W2 from here will be equal to Q minus Q2 as we have already seen. Okay, और जो second refrigerator that is working between T and T1, okay, this is taking heat Q, releasing heat Q1 such that this Q1 will be equal to W1 plus Q, or you can say this W1 will be equal to Q1 minus Q. Getting this or not? Okay, now what will be the COP of the two refrigerators? So COP of refrigerator 1, this will be equal to COP of refrigerator 1, desired effect upon work transfer. So this can be written as T, lower temperature is T, divided by T1 minus T. Okay, similarly, or further this can be written as this will be equal to C1 is equal to 1 upon T1 by T minus 1, or you can say T1 by T is equal to 1 by C1 plus 1. Clear or not? Okay, similarly about C2, so what will be C2? COP of refrigerator 2, this will be equal to T2 upon T minus T2. Yes. Okay, further this can be written as 1 by T by T2 minus 1, or you can say T by T2 is equal to 1 by C2 plus 1. Getting this or not? Okay, so T1 by T is this and T by T2 is this. Clear or not? Okay, now first what we will do is for equal work input. Okay, so for equal work input, same thing what we have done in case of engines. So for equal work input, okay, W1 is equal to W2, or you can say Q1 minus Q is equal to Q minus Q2, and I am directly writing it as T1 minus T is equal to T minus T2, or you can say this T will be equal to T1 plus T2 by 2. Same thing, same result we are getting. Okay, so इसलिए याद करने में भी प्रॉब्लम नहीं बहुत ज़्यादा. For equal work input, the intermediate temperature is the arithmetic mean of the two temperatures. Intermediate temperature is the arithmetic mean of the two temperatures. Similarly for equal COPs, okay, for equal COP, that means if C1 is equal to C2, or you can say C1 is equal to C2 means this will be equal to T by T1 minus T is equal to C2 is equal to T2 upon T minus T2. Okay, or you can say this will be equal to T square. Okay, just multiply this by into minus T into T2, this will be equal to T1 T2. Okay, T1 T2 minus T into T2. Okay, so this minus T T2 minus T T2, this will be cancelled out, and finally we will get what? So from here this will be equal to T is equal to under root of T1 T2. Okay, so this is for equal efficiency, sorry, for equal COPs. Okay, so same result we are getting for equal work input. The temperature, intermediate temperature is the arithmetic mean of the two temperature, and for equal COPs, intermediate temperature is the geometric mean of the two temperature. Same result we are getting. Okay, now what about overall COP? Now what about overall COP? So this overall COP will be equal to T2 upon T1 minus T2. Okay, lowest temperature is T2, higher temperature is T1, T2 upon T1 minus T2. Okay, now further this can be written as C0 is equal to 1 upon T1 by T2 minus 1, or you can say this T1 by T2 is equal to 1 by C0 plus 1. That's it. Getting this or not? Okay, now further this T1 by T2 can be written as T1 by T into T by T2. Okay, and we have already derived this T1 by T2 can be written as 1 plus 1 by C0, okay, is equal to T1 by T can be written as 1 plus 1 by C1 into 1 plus 1 by C2. That's it. Okay, so this is how we can determine overall COP of the coupled refrigerator. Getting this now? Okay, same thing you can do it for the heat pumps as well. I am leaving this up to you. For heat pumps as well, you can do same thing, and you will get the same result in case of for equal work input, you will get the temperature, intermediate temperature as the arithmetic mean of the two temperatures, and for equal COPs you will get the intermediate temperature as geometric mean of the two temperature. There will be some difference in case of overall COP. I will tell you what difference you will get. Overall COP of coupled heat pump. Okay, rest you can do it by yourself. Overall COP, this will be 1 minus 1 by C naught. This will be equal to 1 minus 1 by C1 into 1 minus 1 by C2. That's it. This will be the overall COP for heat pump. Clear or not? Okay. Now again, very important note, same analysis which we have done in case of engine, we will do it here. Now let's suppose C1 is equal to 2 and C2 is equal to 3. That means COP of refrigerator 1 is 2, COP of refrigerator 2 is 3. Now what will happen? So this 1 plus 1 by C naught is equal to 1 plus 1 by 2 into 1 plus 1 by 3. Now this can be further written as this will be 3 by 2, this will be 4 by 3, 3 will be cancelled out, this will be 2. Okay, or you can say 1 by C naught is equal to 1 or C naught is equal to 1. That means overall COP of this refrigerator will always be less than the COP of the individual refrigerator. In case of heat engine, we got the result that the overall efficiency of the heat engine is greater than that of the individual efficiencies. In case of refrigerator and in case of heat pump as well, आप इसको heat pump के लिए भी कर सकते हैं. In case of refrigerator and heat pump, you will get what? Overall COP of the refrigerator or heat pump will always be less than that of the individual COPs. ओके, सो अगर आपको ये क्वेश्चन आता है, सपोज इस तरीके से कई बार क्वेश्चन फ्रेम हो सकते हैं दैट COP ऑफ रेफ्रिजरेटर 1 इज दिस मच, COP ऑफ रेफ्रिजरेटर 2 इज दिस मच, देन व्हाट विल बी द ओवरऑल COP, एंड यू गेट सपोज 4 आंसर्स, 4 ऑप्शंस, एंड आउट ऑफ विच सिर्फ एक ही ऑप्शन ऐसा दिख रहा है जो कि कम है. सो डायरेक्टली यू कैन टिक दैट और टिक दैट ऑप्शन. ओके, दोनों के COP से जो कम होगा वही ऑप्शन आपका सही ऑप्शन होगा, बिकॉज ओवरऑल COP of the coupled refrigerator is always less than that of the individual COPs. Getting this or not? Now let's suppose question इस तरीके से फ्रेम होता है that as I told you the example, let's suppose the COP of refrigerator 1 is suppose 2 and COP of refrigerator 2 is let's suppose 3. Then what will be the overall COP of the refrigerator? And option given are 1, 2, 3 and 4. Okay, now you know one thing, you don't need to calculate this. Okay, for this particular option, set of options, you don't need to calculate this. What you can conclude is overall COP will always be less. Okay, so 2 is not less, that is equal to one of the COP of the refrigerator, 3 is also equal to another COP of refrigerator, and 4 is greater than the both COPs. So obviously the answer should be A, which is 1, because only 1 is the option which is less than that of the individual COPs. So this you can treat as a shortcut as well, but for the particular set of options only, not for all. अगर मान लो की बात एक से ज़्यादा अगर आपके पास ऑप्शन कम आते हैं individual COPs से, then obviously you will have to calculate. Getting this or not? Now I will tell you one very interesting investigation by a scientist whose name was Lord Kelvin. What he did was, in cold countries the temperature is, as we know, is minus 10 degrees centigrade, minus 15, minus 20 degrees centigrade. Okay, so they have to heat their houses. किसी तरीके से उनको अपने घरों को गर्म रखना पड़ता है. So one of the way is they can burn the fire and they can burn the fuel, and whatever heat they are getting from burning the fuel, that can be used in order to heat the house or heat the room. This is the one way. Now can there be any way, now in this particular process, whatever heat I am getting from burning the fuel, suppose Q1 amount of heat I am getting from burning the fuel, the same heat will be utilized, can be utilized to heat the house. Now can there be any way in which the heat which I am supplying can be multiplied manifold and can be utilized in many more times? So for this he devised one thing, one engine. So what he did was, this is the higher temperature source from where we are supplying heat. Okay, so this heat is first transferred to the heat engine. Just understand this arrangement very carefully. Okay, initially जो heat हमको मिल रही है from burning the fuel, that we are transferring it to the heat engine. Okay, this heat engine obviously will perform certain work and it will reject some heat. Let's suppose Q2 amount of heat it is rejecting to a temperature T, which actually is the desired temperature, the room temperature. This T is the room temperature which we have to maintain. a higher temperature which we have to maintain. Getting this now? Okay. Now, what he did was, from this work obviously is equal to Q1 minus Q, sorry, this is Q1, so this work will be equal to Q1 minus Q2. Okay. Now, what he did was, by using this work, he put a heat pump, okay, और इसका जो heat engine का जो work मिल रहा है, he fed that work to the heat pump and he ran that heat pump between the lower temperature sink, which is atmosphere is at very lower temperature, और उसके बीच में और रूम के बीच में इसने एक हीट पंप चला दिया. ओके, आई विल एक्सप्लेन यू अगेन. दिस इज हायर टेम्परेचर सोर्स. लेट सपोज हम कुछ फ्यूल को बर्न कर रहे हैं जिसमें से हमको हीट मिल रही है. लेट सपोज Q1 अमाउंट ऑफ हीट वी आर गेटिंग, हाई टेम्परेचर सोर्स. By using this high temperature source, we are getting heat Q1, and by using this Q1, we are running one heat engine between this higher temperature source and between our room temperature. इन दोनों के बीच में पहले एक heat engine रन हुई, उसमें से जो भी वर्क मिला हमको Q1 minus Q2 अमाउंट ऑफ वर्क मिला, that work is fed to the heat pump, and this heat pump was running between the lower temperature source, lower temperature sink you can call, that means atmospheric temperature, बाहर का टेम्परेचर जो कि -5 -10 डिग्री सेंटीग्रेड है, उस टेम्परेचर और रूम के टेम्परेचर के बीच में हीट पंप चला दिया हमने. तो उससे हुआ क्या, फ्रॉम हियर दिस इज टेकिंग सपोज Q2 अमाउंट ऑफ हीट, लेट सपोज दिस इज टेम्परेचर इज T3, दिस इज T2, दिस इज टेकिंग Q3 अमाउंट ऑफ हीट, और यहाँ से लेट सपोज Q2 डैश अमाउंट ऑफ हीट ये जा रही है और ये वर्क ले रहा है W, विच इज इक्वल टू Q1 माइनस Q2. गेटिंग दिस नॉट? ओके, सो आई थिंक दिस अरेंजमेंट इज क्लियर. सो व्हाट ही फाउंड वाज समथिंग वेरी इंटरेस्टिंग. इनिशियली जो Q1 हीट थी, अगर मैं डायरेक्टली किसी फ्यूल को बर्न कर रहा हूँ, आई एम गेटिंग दिस Q1 हीट इन द रूम, बट बाय यूजिंग दिस अरेंजमेंट व्हाट आई एम गेटिंग इज Q2 प्लस Q2 डैश हीट. दिस मच हीट इज सप्लाइड टू द रूम. यहाँ से Q2, यहाँ से Q2 डैश, दिस मच हीट इज सप्लाइड टू द रूम. नाउ व्हाट ही फाउंड वाज दिस Q2 प्लस Q2 डैश इज वेरी ग्रेटर देन द अमाउंट ऑफ हीट Q1. ओके, दैट मीन्स इनिशियली जो हम हीट अलग से हमने कुछ किया नहीं, अलग से और एनर्जी सप्लाई नहीं कर रहे हैं, जितनी हीट हम Q1 यूज़ कर रहे थे उसी को यूज़ करके हमने ये डिवाइस रन की, एंड वी फाउंड दैट इन दिस रूम नाउ वी आर गेटिंग Q2 प्लस Q2 डैश हीट विच इज मच ग्रेटर देन दिस Q1. ओके, और इसका जो रेशियो है, दैट मीन्स Q2 प्लस Q2 डैश डिवाइडेड बाय Q1, दिस रेशियो ही नेम्ड एज मल्टीप्लिकेशन फैक्टर. So now we will derive this value of this multiplication factor. What will be the value of this multiplication factor? We are assuming this heat engine and heat pump to be reversible. So what will be the efficiency of this heat engine? So efficiency of this heat engine, as we know, is 1 minus Q2 by Q1. And because this is a reversible heat engine, so this efficiency will also be equal to 1 minus T2 by T1. Or you can say Q2 by Q1 is equal to T2 by T1. Or you can say Q2 is equal to Q1 into T2 by T1. Okay, this is suppose equation number 1. First thing, getting this? Okay, now for this particular heat pump, the COP of heat pump, as we know, is desired effect upon work input. Desired effect here is Q2 dash, higher temperature desired hai, so desired effect here will be equal to Q2 dash divided by work input. And what is this work input? This work input is nothing but Q1 minus Q2, so you can write this as, so this will be equal to Q2 dash upon Q1 minus Q2, and this is also equal to, because this is a reversible heat pump, this is also equal to T2 upon T2 minus T3. Getting this or not? Okay, now further this can be written as this Q2 dash will be equal to T2 upon T2 minus T3 into Q1 minus Q2. And what is this Q2? This Q2 can be further written as Q1 into T2 by T1. What we are doing is we are converting this in the form of Q1, so that further we can cancel this. यहाँ से हमको Q2 है, Q2 डैश है, तो Q2 को हमने पहले Q1 के फॉर्म में किया, Q2 डैश को भी हम Q1 के फॉर्म में कर रहे हैं, so that Q1 की वैल्यू सेपरेट हो जाए, and we will get the answer in terms of T1 T2 only. Getting this not? Okay, so this Q2 is equal to T2 by T2 minus T3 into Q1. Further this can be written as Q2 dash is equal to Q1 into, this will be T2 upon T2 minus T3 into 1 minus T1 T2 by T1. Getting this now? Okay, now further this can be written as, I will write this here, so further this can be written as this Q2 dash will be equal to Q1 into, this will be T2 by T1, T2 by T1 into, okay, here न्यूमरेटर में क्या आएगा, it will be T1 minus T2, डिनोमिनेटर में T2 minus T3, T1 minus T2 upon T2 minus T3. Getting this? This is the value of Q2 dash. Okay, so now we have the value of this Q2, we have the value of this Q2 dash, we can easily determine the value of this multiplication factor. Now what will be this multiplication factor? So I will rub this. Okay, so this multiplication factor, as we know, is Q2 plus Q2 dash divided by Q1. So this can be written as, this will be Q2 can be written as Q1 into T2 by T1 plus Q2 dash, this can be written as Q1 into T2 by T1 into T1 minus T2 upon T2 minus T3, okay, divided by Q1. Okay, so this Q1 will be cancelled out. Okay, and if you take this as common, you will get T2 by T1 into 1 plus T1 minus T2 upon T2 minus T3. Okay, so this will be T2 by T1, T2 minus T3 plus T1 minus T2 divided by T2 minus T3. Okay, so from here this T2 will be cancelled out and you will get what, this multiplication factor will be equal to T2 minus T1 into T1 minus T3 divided by T2 minus T3. That's it. Okay, so this is the value of this multiplication factor. Clear or not? Okay. Now with the help of one example, I will explain you the importance of this multiplication factor. This multiplication factor का आखिर importance क्या है? You will very soon understand. Now let's suppose we are considering one example. Let's suppose T1 temperature is given as 400 degrees centigrade, T2 temperature is given as 20 degrees centigrade and T3 temperature is given as, let's suppose, minus 20 degrees centigrade. We have to determine the value of this multiplication factor. Okay. Now just put the value. This multiplication factor will be equal to, this will be T2 by T1. So this will be 20 degrees centigrade in terms of Kelvin. This will be 293 divided by 400 plus 273 is 673 into T1 minus T3. This will be 673 minus T3. Okay, 273 minus 20 is 253 divided by T2 minus T3. Okay, so this will be 20 means 293 minus 253. Getting this? And on calculating this, you will get this multiplication factor as 4.57. Okay. Now, इसका मतलब समझ में आ रहा है, मल्टीप्लिकेशन फैक्टर इज इक्वल टू 4.57. मल्टीप्लिकेशन फैक्टर हमने कैसे डिफाइन किया? दिस मल्टीप्लिकेशन फैक्टर इज नथिंग बट द रेशियो ऑफ Q2 प्लस Q2 डैश डिवाइडेड बाय Q1. ओके, दैट मीन्स Q1 से ये कितना ज़्यादा है, Q2 प्लस Q2 डैश कितना ज़्यादा है, इस पर्टिकुलर केस में 4.57 टाइम्स मोर. व्हाट डज दिस मीन? दिस मीन्स डैट अगर हम जो हीट मुझे 1 किलो जूल मिल रही थी एक सिंपल अरेंजमेंट से, अगर मैं सिंपली आग जला रहा हूँ अपने रूम में and I'm burning some fuel and I'm getting Q1 amount of heat. Okay, 1 किलो जूल अगर मैं जला रहा हूँ तो 1 किलो जूल की हीट मुझे मिलेगी. But by using this device, I'm getting how much heat? Q2 plus Q2 dash heat, which is actually 4.57 times more than that of this Q1. इसका मतलब क्या हुआ? इसका मतलब ये हुआ that I am giving 1 kilojoule of heat, but I am getting 4.57 kilojoules of heat. This is the importance of this device. This was devised by Lord Kelvin. Getting this now? So this is nothing but the multiplication factor. Clear? Now next very important point about this Carnot engine is this Carnot engines are used to define thermodynamic temperature scales. Okay, Carnot engines are used to define thermodynamic temperature scales. Or you can say this Carnot engine can be used to calculate temperatures as well. This can serve as a thermometer as well. Now how can this, with the help of this Carnot engine, we can calculate temperature? I will tell you. Okay, so let's suppose we are having this Carnot engine, and we know for this Carnot engine or reversible engine, what we know is this Q1 by Q2 is equal to T1 by T2. We have already discussed. Now just understand this point very carefully. Now out of these two temperatures, Q1 by Q2 is equal to T1 by T2. Let's suppose I am fixing any one temperature as triple point of water. Okay, any known temperature. So we know the value of triple point of water, which is 273.16 Kelvin. Now let's suppose I am fixing this temperature, any temperature, I am fixing it to the triple point of water. Okay, that means this temperature is known, or I can say, let's suppose the heat interaction is Q and Q naught. This is equal to T and T naught. This T naught is nothing but triple point of water, which we know. Okay, now if I know this temperature, just with the just by knowing the interaction of heat. Okay, simply मैं heat interaction अगर मुझे पता है, then I can calculate this unknown temperature. Getting this or not? Okay, that means हमने thermometer में भी यही चीज़ देखी थी. In all thermometers we use certain thermometric properties. Let's suppose in liquid in glass thermometer, उसमें thermometric property हमने क्या use किया था? Volume. Okay, with the help of change in volume we calculated the temperature. Okay, इसमें क्या किया था हमने? Simply हम we were measuring the volume change only. How much volume of mercury is getting changed. Same thing अगर मैं इसमें simply अगर मैं heat change, heat exchange measure कर लूँ और कोई एक टेम्परेचर को अगर मैं फिक्स कर लूँ, आई विल बी एबल टू कैलकुलेट द unknown temperature. Okay, from here this T can be calculated, which is equal to Q by Q naught into T naught. Let's suppose this is T naught, this is let's suppose T, this is Q and this is Q naught. Okay, so just by calculating the heat interaction I can calculate the unknown temperature. Okay, so this Carnot engine can be used to measure the temperature, and this can also be used to define the temperature scale. Now how can we define any temperature scale with the help of this Carnot Carnot engine? I will just tell you with the help of one example. Now just read this question. 20 kilojoule of heat is transferred at 100 degree centigrade and 14.64 kilojoule of heat is rejected at 0 degree centigrade. What is the value of absolute zero on this thermodynamic temperature scale? Now what is given is we are having an engine, a Carnot engine, okay, such that in this at 100 degree centigrade 20 kilojoule of heat is supplied to the engine and it is rejected at 0 degree centigrade. How much heat? 14.64 kilojoule of heat is rejected. Obviously some work will be produced. Now with the help of the given information, now what we are given is just the temperatures at two different temperature. What are the heat interactions that is given in a Carnot cycle? Now with the help of this we can find out the absolute zero in this particular temperature scale. Now obviously here it is given in centigrade. We know in centigrade the absolute zero lies at -273 degree centigrade. But maybe हो सकता है कि ये किसी और यूनिट में भी दे दे, हो सकता है any unknown unit, let's suppose रो में ये चीज़ दे दे. So just with the help of knowing the temperatures, दो पॉइंट का टेम्परेचर अगर हमको पता है और उन दोनों पॉइंट्स में कितनी हीट इंट्रैक्शन हो रही है, if we know that, we can calculate the absolute zero in that particular temperature scale. Now how can we calculate? I will tell you. So we have, if I plot this graph between heat and temperature, between Q and T, okay, now at 0 degree centigrade the heat interaction is 14.64. So this will lie somewhere here. This is 0 degree centigrade line and this is centigrade line in degree centigrade. Okay, this is 14.64. This value is given as 14.64. Okay, and at 20 degree and 20 kilojoule of heat is supplied at 100 degree centigrade. Okay, so this point will lie somewhere here at 100 degree centigrade. This point is at 100 degree centigrade. Okay, and at this particular point the heat supplied is 20 kilojoule. This is 14.64 kilojoule and this is 20 kilojoule. 20 kilojoule. Okay, if I join this with the help of a linear line, now what I have to do is I have to find out the absolute zero in this particular temperature scale. Now how can we determine the absolute zero in this particular temperature scale? So what we can do is I can extend this. Okay, जब तक कि y का point zero नहीं होता, I can extend this and at this particular point this is nothing but absolute zero temperature. Getting this or not? तो इस particular ये particular point हमको निकालना है कि यहाँ का temperature कितना होगा. That we have to determine absolute zero temperature. In this particular temperature scales, ये क्या बोल रहा है? 20 kilojoule heat supply हो रही है या reject हो रही है 100 degree centigrade से और 14.64 kilojoule of heat is heat interaction is there at 0 degree centigrade. So with the help of this we are calculating this absolute zero. Okay, now what we can do here is this is 20, this is 20. This is 14.64. We can take this similar triangle. Let's suppose this is O, A, B, C and D. Now this triangle OAB is similar to triangle OCD. Yes, OAB is similar to triangle OCD. Getting this now? Okay. Now what we can write it as right now is AB upon OB. This upon this is equal to CD upon OD. Getting this? Now AB as we know is 14.64 divided by OB. What is this OB? Just we have to determine, is equal to CD, we know is how much? 20 divided by OD, which is nothing but OB plus OD plus BD, sorry, OB plus BD. This point is B, this point is B, this is O. Okay, so this is OB plus BD. Getting this now? And BD as we know is 100, तो इसको हम replace कर सकते हैं यहाँ पर 100 से. Just one unknown we are having, that is OB. So when you calculate this OB from here, you will get this OB as 273. Okay, the value of this OB is nothing but 273. अब ये 273 है, this whole distance is 273. Now what does this mean? This means that this point will lie at minus 273 degrees centigrade. That means absolute zero temperature at Kelvin scale is at minus 273 degrees centigrade. So as I told you, because this was a centigrade scale, and we know already about centigrade scale that absolute zero lies at minus 273 degrees centigrade. But let's suppose in any other unit it would have been given. Then with the help of just the heat interaction with the temperature, we can determine the value of absolute zero in that particular temperature scale. Hence it is said that Carnot engines are used to define the thermodynamic temperature scales. Getting this or not? Okay, thank you so much.